Hello, everyone. Welcome to our class, Computational Thinking. My name is Hüseyin Kuyumcuoğlu, and I will be teaching the first three classes of the whole Computational Thinking class. So let's get started. So what's computational thinking? This should be the first question that comes to your mind, right? The term computational thinking was first used by Seymour Papert in 1980, but it was actually popularized by computer scientist Janet Wing, as you can see in the picture on the right-hand side, in an article that she wrote in 2006. Here are two quotes from her article. I think we can benefit from these quotes to understand what computational thinking is. Wing says, computational thinking is a way humans solve problems. It's not trying to get humans to think like computers. And here's another quote from her article that she wrote in 2014. Computational thinking will be a fundamental skill used by everyone in the world by the middle of 21st century. By fundamental, I mean as fundamental as reading, writing, and arithmetic. As you can see, it's a very high expectation from people that everybody will be using computational thinking as they use arithmetic and reading and writing. So let's get started understanding what computational thinking is comprised of so that we can see whether we can reach such an ideal. Okay. Before trying to understand what computational thinking is, and besides that, although computational thinking does not necessarily involve using a computer to solve a problem, we usually benefit from computers in solving our issues. Think of usage of computers in our life. There are you can probably count numerous usages in our life. Some of them are we use computers for social interactions. We use them for social media or like communicating with each other in all sorts of different ways. We use computers for managing our finances, getting news, reading books. We get all information, most of our information through computers today, either through social media or by other means. We use computers for doing all sorts of office work or all sorts of computerized farm machinery and drones, or in automated factories. So computers, I mean, we use personalized computers for our personal individual uses, but we use drones and automated factories for communal usages of computers. So computers have a fundamental place in our social life. That's undeniably true. How about computational thinking? As I said, computational thinking is a method for problem solving. The solution to a problem may or may not involve a computer. Nevertheless, we need to incorporate computers to solve large problems that we face today. So computational thinking does not necessarily involve a computer to solve a problem. It's a way of thinking. But we need to involve computers in solving our problems that we face today, because the problems that we face today are huge problems, and we need help from computational power of all sorts of computers today. There's a problem that we want to solve. We apply computational thinking. We usually benefit from computers as well, and we reach a solution. There are four major elements of computational thinking. When you say computational thinking, or when you search for it in any medium, these four elements will be the major elements that you'll be facing: problem decomposition, pattern recognition, abstraction, and algorithm. So what are these components? You will have more chance to learn about these components in the coming classes throughout the semester, but let me just go over them very, very briefly. Problem decomposition. First, when we are solving a problem, we decompose a problem into smaller problems to target these small problems first, only later to combine these solutions to solve the larger problem. And that's how you engage with problem decomposition. On the second step, when we deal with these smaller problems, we will reuse similar solutions. We will benefit from these similarities in our solution to the larger problem. And that's what we call pattern recognition. On the third step, while solving a particular problem, we will need to ignore some information and focus on others. And that we call abstraction. We will abstract certain data or certain issues from others. We will exclude some problems or attributes and focus on certain others, and we will call this step abstraction. And finally, we will develop the rules that we need to follow towards a solution, and we will call this step algorithm. Okay, let me move on. So now let me show you a video about how computational thinking might be used in one of the largest companies today. Let me just turn off my video and leave you along with this.
Computational thinking. Computational thinking is a set of problem-solving techniques that we use here at Google. One aspect of computational thinking is decomposition, where we take a large problem and we break it down into smaller pieces. Another aspect is pattern recognition. We use pattern recognition to help us identify similarities and differences. The final part of computational thinking is algorithmic design. That allows us to create a step-by-step strategy for solving a problem. Google Earth is a perfect example of computational thinking because it takes a large problem of trying to visualize the entire planet and makes it so that anybody can explore the world around them.
Google Earth is basically an attempt to recreate the whole world in 3D. And we want to make it as if it's the real world. We don't want to make anything up. We don't want to create anything or invent anything. We want to make it the real world. And initially, it seems like this crazy problem if you really think about it. The world is huge. It takes a tremendous amount of data. If we were to try to send this to you, we'd have to pull up in front of your house with tractor trailers full of hard drives of all the images. So it seems kind of impossible, but we make it possible. In school, you're given these problems that are very black and white. You know, you either have the answer or you don't have the answer. You got it right or you got it wrong. In the real world, there are many right answers.
Google Maps is a collection of imagery and data about places and roads all around the world. And using Street View, we actually have images from cars right along all of the streets. Once we've collected all this imagery, we have to somehow put it together in a way to be able to share it with the world. Not long ago, I started getting annoyed with Pegman. Pegman is the little yellow guy on Google Maps that you can drag to get into Street View. And so you drag Pegman from the corner in Google Maps and you drop him on the street you want to get into and look at. That works great when you know exactly where you want to go, when you want to zoom all the way in on a single address and drop him next to a house or something. But say you just want to go to New York City. When I drag and drop Pegman, he'd fall somewhere, well, somewhere random. In fact, he seems to prefer to land in back alleys. He didn't mind landing in the middle of a field. He'd land on big highways, but he'd almost never land in front of a famous landmark. And if you dropped on Paris, he'd never, ever land on the Eiffel Tower. I thought to myself, we can do better than that. We kind of know what famous places are in the world. We should fix this. I began to think to myself, what makes a panorama, one of these images in Street View, important? And then I thought about it further. I thought, when people go to places that are interesting, when they physically travel there, what do they always do when they're in a famous place? They pull out their camera and start taking pictures. People post a lot of these pictures to the internet. So we could look for places that people take a lot of pictures. We can find things that are in those photographs that people took and see if we can find the same things in the Street View images. And so if we can see the Eiffel Tower in the Street View image and we can see it in a bunch of images people took, we can automatically know that it's probably important. We've worked really hard to make Pegman smarter. When he's dropping from the sky, we want him to land somewhere interesting.
Thinking computationally is a lot more like art than it is like math class. You go in and you know you want to create something and you have a blank canvas and you use math and you use these tools to paint on that canvas and you end up creating something beautiful.
Okay, this was just one example of how computational thinking is used in one of these greatest software companies, as named Google, as you have seen. But just one example. The idea is you can use computational thinking for solving multiple problems. Let me just go forward and try to give you some other examples. And having given the example on Google, you might think that computational thinking is used by software programmers. It's totally false. Its usage is much wider. As you can see in the slide, we can use computational thinking in natural sciences, computational biology, genomics, applied physics, climate change, astronomy, or in social sciences like in social studies, population analysis. We can use it in medicine for disease analysis, medical imaging, clinical practice, or we can use it in linguistics, law, music, teaching, and many others that I haven't put in this slide. Think of climate change. Think of how scientists are working on multiple data to find out how climate change is actually affecting our lives and actually affecting the planet. They work on so much data that it's not possible for anybody to understand that data or to even start working on that data without having a good plan. Scientists have to use patterns. They have to, first of all, decompose the problem into smaller problems, find patterns in those smaller problems, abstract unnecessary data from required ones, and then in the final step only determine the algorithm to solve the problem. So it's not like it's a bunch of software engineers who are trying to solve the climate change problems by these models. You need people who are thinking computationally. Let me show you this video on how scientists are actually working on climate change.
Humans' dependence on fossil fuels is heating up the planet at an unprecedented rate. Governments and policymakers must take urgent action. That action is guided by what science says about the impact of climate change on the Earth. This is how it's calculated. This is Wilhelm Bjerknes. At the end of the 19th century, he devised formulas which linked the flow of heat, water, and air. 50 years later, his ideas were the basis of the first computer model of the atmosphere, and modern-day weather forecasting was born. Today's climate models are the highly evolved descendants of that original, except the computers are some 25 trillion times faster. Here's how it works. Scientists divide the Earth's atmosphere into a grid of hundreds of thousands of cells in stacks like a skyscraper. The model used by the Met Office, Britain's National Weather Service, for example, uses stacks which are 85 cells high. The models then calculate how energy, air, and water vapor flow through each cell over a given time period. While weather forecasting takes a snapshot of the atmosphere at a given time and predicts what will happen over the next few days, climate models consider the atmosphere's behavior over years and years, simulating either the world as it is or the world as it might be.
They sketch out the sort of processes and the sort of results that you might see. And that allows you to inform policy to some extent. One of the classic things that climate models have always done is just look at the world if the carbon dioxide level were twice as high as it is today. That was one of the first ways that climate models began to illustrate the fact that greenhouse warming really was likely to be a problem in the 21st century.
For all their complexity, these models have limitations.
Although you're cutting the atmosphere into millions of cells, the atmosphere is a very big thing, and a millionth of a big thing is still a pretty big thing. So the cells tend to be, they may be hundreds of kilometers on a side.
This means the models often struggle to capture details like cloud cover, and clouds play a key role in climate. As greenhouse gases make the atmosphere warmer, they change the amount of water vapor it can hold and how air rises and falls. That in turn changes the amount and character of cloud cover. Depending on where clouds form, they can either trap sunlight, which warms the planet, or reflect it back into space, cooling it. And some processes which govern cloud formation work on a very small scale.
So you can't actually model those precise processes in the computer model. So you have to build various different rules of thumb in for what would you expect the clouds to be doing. How you do that means that your model will behave differently compared to someone else's model where they do that in a different way.
Dozens of these models exist, run by teams all over the world.
The modelers all want to capture the Earth as close as possible to how it is, but their assumptions about how that actually works differ from model to model, and the ways that they implement those assumptions change. Some models tend to, people say, run hot, so they tend to provide more warming for a given amount of carbon dioxide, and some models tend to run a little cold.
Every few years, the models are brought together, fed standardized questions, and then their results are compared. This helps scientists understand the strengths and weaknesses of different climate models and improves them. Of course, it's impossible to assess the model's future projections, but what researchers can do is compare the success of models from previous decades. A recent report compared the models from the 1970s to the 2000s.
And it found that by and large, they were reasonably good, that the warming that we'd actually seen sat within the error bars for most of them. So it gave you a sort of like general sense that these things weren't completely out of the park.
The climate models are getting increasingly complicated, capturing more aspects of the Earth. But there is one element that is impossible to model, and it is the biggest contributor to climate change.
The thing about human activity is that you can't get it inside the model. The model deals with sort of like physical laws of chemistry and physics and biology. So there's no way the model can say, well, in 2050, America will have stopped emitting carbon dioxide.
Instead, scientists take simplified results from these climate models and run them through economic models. In 2013, scientists used these models to examine the effect of different climate policies on the future temperature of the planet. The first looked at what would happen if there was continued large-scale use of coal. The second, if there was continued use of fossil fuels, but some use of renewable energy. The third, if there was a much higher uptake of renewable energy. And the fourth, if there was a lot of use of carbon capture technology and more land to grow biofuels.
The striking thing about those comparisons, and by other comparisons that have come out later, is that only really tough climate policies get you the sort of trajectories which keep the temperature, in the words of the Paris Agreement, well under 2 degrees above the pre-industrial. What these models tell us is that the current level of emissions reduction is not remotely enough to have any assurance that you'll stay under 2 degrees, even less, or like close to 1.5 degrees.
Climate models don't predict the future, and they're not perfect. There is a long way to go before they fully represent all of Earth's intricate processes. But for now, they are the only way that scientists have of understanding how damaging an increase in carbon dioxide will be for the planet. Ultimately, the solution to climate change won't lie inside models, but rather what humans choose to do with the information they provide.
I'm Oliver Morton. I'm the briefings editor at The Economist.
Okay, that's enough, I think. So as you have seen, it's a very complicated process to find these climate models. And the process is not only about using a computer. It's not about only collecting data and using a computer. First of all, you have to decompose the problem into separate subproblems. And as you have seen in the video, as you should have seen in the video, the problem is not only about guessing physical particles in the air. That's one subproblem. One subproblem is trying to make good forecasting about how physical particles in the atmosphere are moving from one place or another to another place and how they're accumulating in these different places. Another subproblem is finding economic behavior that humans are engaging in, whether they are using fossil fuels, whether they are using carbon capture technology, or whether they are like using only coal in the next 100 years. So these are two major subproblems. That's what the video was trying to explain us. After this process, you take one of these subproblems. Let's say you want to understand and forecast how the physical chemical particles are moving in the atmosphere. You take this subproblem and divide it into further subproblems. You have seen in the beginning of the video that they divided the world's atmosphere into thousands of grids. Grids are like these small units that you divide any shape into. They take the atmosphere and they divide it into small units in the shape of a skyscraper, and they divide that skyscraper into further pieces. They further decompose the problem. That was the first step in computational thinking. Later, they found patterns in these subproblems. Each of these levels in the skyscraper grid will probably work in similar ways. At least their analysis will be done through similar methodologies. You will probably investigate similar chemical and physical particles. You will use similar computer models in each of these levels in skyscraper grids, and each skyscraper grid will make up the whole grid that encompasses the world's atmosphere. So in that sense, you use pattern recognition, and you try to use a single pattern and try to find out the whole pattern for the whole atmosphere. And you use also data abstraction. You try to focus on certain physical and chemical particles when you are investigating one level in that skyscraper-shaped scale, in the skyscraper-shaped grid. You focus on certain particles that are making up the world's atmosphere and that are relevant to climate change. You are not focusing on all sorts of particles. So you are excluding certain particles and taking certain particles into your calculation. You are abstracting certain data. Finally, you come to the level of algorithm. You take help from computers at this level in a problem like climate change, and you use computer models to create those graphs that you have seen in the picture. So this is a very good example of how you can use computational thinking to solve, or at least try to tackle with, a huge problem like climate change. Some other problems. A similar approach could be used in refugee problems, for instance. Remember very recently, thousands of refugees were fleeing away from war zones, especially in the Middle East, but also in other parts of the world as well. And you need to understand how you can divide this problem into sub-problems. You probably have to look into either war zones or countries to divide the problem into sub-problems, and understand which problem can be divided into what further problems, and try to find out patterns among these different refugee problems. Each country have refugees for different reasons, give out refugees for different reasons. Some people are running away from war zones, some people are running away from famine, and etc. There are multiple reasons for this. There will be, scientists are guessing that there will be climate refugees in the near future. People will be running away from the effects of climate change. And like in the previous problem, you will have to benefit from computer models and graphs, as you can see in the picture, to find out how you can address the numerical aspects of these problems. This is also a very big problem that you benefit from computational thinking. There's a rather new emerging field called computational law. It's mostly legal scholars or lawyers even thinking that, okay, they don't have much to do with computation. They don't have much to do with softwares, computation, or even computational thinking. It's been increasingly proven wrong with this emerging field that we call computational law. Computational law is the branch of legal informatics concerned with the mechanization of legal reasoning. The primary focus of work in the field is the development and deployment of computer systems capable of assessing, facilitating, and enforcing compliance with specific sets of regulations. And sometimes judges even use these computer systems, computational systems, as this decision support systems. They do not leave all the decision to a computer, of course. A computer cannot decide as if they were a human judge, but human judges benefit from decision support systems that are benefiting from, again, computational thinking and softwares that help judges analyze the problem into further details. Another usage of computational thinking is medical diagnosis. As you have already probably witnessed yourself even, we have multiple visuals and data in all these medical centers that doctors have difficulty to analyze if they weren't taking any help from computers. So taking help from computers, as I said, is only one aspect of computational thinking. The major elements of computational thinking point at how people are thinking when they think computationally. Pattern recognition, from the beginning, problem decomposition, pattern recognition, data abstraction, and algorithm. All these four major steps require a way of thinking. It's not only how softwares are running behind our tasks. So let's look at this example from a medical diagnosis.
Hospitals are producing so much data that it is extraordinarily difficult to provide the analytics of it so that we can actually benefit patients going forward.
We're collecting a lot more data on these patients, but we're only scratching the surface of how that can be used in the sense of decreasing critical illness. There are always better ways for us to improve the outcomes.
And so artificial intelligence allows us to take information from tens of thousands of patients in order to predict what's going to happen to this particular patient and to prevent it from happening. The Bronx is a very interesting community of people. It is the most vibrant urban environment, I think, in the United States, but it also happens to be the poorest urban county in the country. For a system like Montefiore's, we have to be able to deliver care extraordinarily efficiently because the amount that we get paid to do that is very, very low relative to the costs of delivering that care.
The reality is patients in the hospital are much sicker than 10, even 20 years ago. The most severe type of respiratory failure is ARDS, and upwards of 40% of the patients of ARDS may not survive the hospitalization. These patients often need ventilators. They often need to be in the ICU for long periods of time. And what we wanted to be able to do was to find a way of detecting patients who may be at high risk of developing respiratory failure.
The way to do that is the use of data that exists in thousands and thousands of patients to predict who's at risk and to intervene to prevent it from happening.
I'm finding patterns in the data, finding patterns that otherwise are much harder to find, but we're using the data to tell us where those objects are instead of trying to look for them manually.
We are using machine learning and artificial intelligence to build a system that's always watching. We call it PALM, Patient-Centered Analytic Learning Machine. Our vision is to present PALM as the nervous system of this institution.
So it's tricky to detect respiratory failure. Respiratory failure can develop slowly and insidiously.
So what we have designed PALM to do is that it collects different kinds of information.
Someone's heart rate, their blood pressure, their oxygen saturation, changes in their physiologic vital signs on a second-by-second or minute-by-minute basis has implications for where they are going.
PALM's job is to calculate the risk for the patients to have either respiratory failure or whether or not this patient is at risk of dying.
There is an overwhelming amount of data that we have to deal with in healthcare.
The only way we're going to be able to analyze it is through the use of machines.
So we have found a lot of reasons to work with Intel because they want to not only imagine the future, but also shape the future of healthcare. We are not only using their engineering powers today, we are also using the cluster of servers as underpinning of our technology. It's also having a partner to imagine what is possible in the future. Our algorithm outperforms any similar model that exists. Not only we ended up with an algorithm that can predict respiratory failure, but also it can predict sepsis. We have data that shows that it has decreased the length of stay overall, as well as within the ICU. We see it as the future of healthcare. Our work, it is all about providing the best care possible to the Bronx population.
The thing that's going to distinguish healthcare institutions that are extraordinary from other kinds of healthcare institutions are going to be the ability to recognize the information that they're generating and to use that information productively for patient care. The ultimate goal of this kind of technology is going to be in essentially the cost and the efficiency and the safety of the care that we deliver.
Early treatment is really key in improving outcomes. What excites me about this project is its possibilities in the sense of decreasing critical illness. What we want to be able to see is patients continue to live their lives the way that they want to.
Our job at Montefiore is to pioneer it so that others can take a look at what we've done and say, yes, I can think of ways to apply it to things that Montefiore hasn't even done.
Okay, I think it's enough. And again, in this example, we see how computational thinking can be used to decompose the problem, find patterns, abstract unnecessary data, and finally work on the algorithm to solve a complicated problem, which is in this case medical diagnosis. In this example, the patients were like the software was collecting multiple data from patients, second by second, minute by minute, as the doctor in the video was saying, and they are making forecasts. They are making some guesses about the patient, change in patients, or rather the individual's health situation, and trying to prevent diseases that are forthcoming. So in that sense, we are benefiting from computational thinking for solving multiple difficult problems. These were only some of these examples. throughout this class, throughout the semester, you'll see many such examples, and you actually will be working on some of these examples yourself. And you'll understand it much better how computational thinking should be a basic human skill, as Janet Wing was saying that I showed at the beginning of this class. Starting with next class, you'll be with me in the first 3 weeks, including this week. So in class 2 and class 3, when we discuss logical thinking and critical thinking, we will see how computational thinking should be supplemented by these ancient methods of reasoning. Logical thinking and critical thinking are ancient methods of reasoning that are coming from ancient Greece. And we will be seeing how computational thinking, all these 4 steps, should be supplemented by these ideas. After that, in the following classes, you'll focus more on problem decomposition, pattern recognition, and abstraction. And then we'll have a midterm. And after that, you'll work more on algorithm side. So as I said, there are 4 steps in computational thinking. And after the midterm, you'll work harder on the algorithm side to understand how you can learn, actually to build upon what you have learned before the midterm and apply all that information in a computer system. And you'll be actually coding yourself to find out solutions to the problems given by your instructors. I hope this will be an interesting semester, and I'm hoping to see you in the coming weeks.